Over the last century, engineers have pushed high-speed railways across some of the most unforgiving terrain on Earth, carving routes through mountain peaks and suspending steel tracks over vast gorges. But the deep ocean floor remains a uniquely hostile environment. Down here, total darkness meets crushing hydrostatic pressure, creating conditions that actively destroy human machinery. Until now, crossing the sea by rail meant burrowing beneath it. Passengers had to be sealed inside heavy, claustrophobic tubes of reinforced steel and solid stone, buried safely within the bedrock below the water. Attempting to cross a seismically active, high-pressure trench without that massive terrestrial shield sounds like a structural suicide mission. It is truly the ultimate survival challenge. Yet a visionary megaproject proposed for Japan imagines exactly that: a fully transparent, high-speed rail corridor suspended directly in the cold northern waters off the coast. While it looks like an illustration from a science fiction novel, the design relies strictly on modern, extreme environment engineering logic rather than fantasy. The central problem is entirely physical: finding a way to protect a fragile, glass-walled passenger tube from instantly imploding under the immense weight of the ocean. Turning this concept into reality requires reverse engineering the ocean's physical forces, resulting in a precise, mathematically viable blueprint for modular construction. Before any material touches the water, survey crews must map the invisible seabed. Sonar scanners and remotely operated vehicles sweep the ocean floor, analyzing slope stability and current strength to locate solid rock layers. With the route charted, landside construction begins. Heavy excavators carve downward from the coast toward the sea, forming massive, reinforced concrete approach tunnels. Inside these terrestrial passages, crews install heavy-duty traditional supports. They line the walls with waterproof membranes, drive rock bolts deep into the surrounding stone, and pour thick concrete casings. These dark, heavy sections are non-negotiable. They act as the rigid backbone of the entire system, firmly anchoring the structure so the more vulnerable oceanic sections are not ripped apart by tidal shifts. Miles away, inside massive coastal fabrication facilities, the transparent oceanic sections are assembled as prefabricated modules. This diagram illustrates why the geometry here is a matter of life and death. If built as flat glass boxes, the water pressure would immediately crush the sides inward. By engineering them as perfect circles, the external pressure distributes evenly across the entire circumference. To hold that shape, each module requires a load-bearing internal skeleton. Machined titanium rings and longitudinal ribs interlock to form a rigid, unyielding frame. Next, thick, multi-layer curved glass panels are carefully lowered into the gaps between the metal ribs. Crews manually seal every seam with waterproof polymer gaskets and apply layers of industrial anti-leak gel. Finally, the completed tube undergoes a rigorous pass-fail trial in a deep ocean simulation chamber. Engineers subject the module to extreme artificial pressure, scanning the hull for microscopic glass stress or flange deformation. By combining strict circular geometry with this specific hybrid material science, the crushing forces of the deep ocean are neutralized long before the structure ever reaches the shoreline. Out on the open water, a massive offshore fleet of floating cranes and underwater robots gathers directly above the planned route. The first transparent cylindrical module is hoisted over the side of a barge and lowered slowly through the water column, descending toward the anti-scour rock foundations laid on the seabed. Down in the darkness, robotic arms guide the descending module, aligning its locking grooves. Once it settles, hydraulic clamps engage, permanently locking the support shoes to the heavy anchor bases. The process repeats sequentially. As each new segment drops into place, massive waterproof gasket rings are tightly compressed between the circular end flanges of the two modules, forging an airtight seal. With the tunnel shell connected, crews move inside to install the internal survival systems. They wire in automated sump pumps and fit heavy emergency flood doors precisely at the transition zones where the glass modules meet the concrete tunnels. Then comes the railbed. Steel tracks are aligned precisely over heavy-duty vibration isolation pads, absorbing kinetic energy to ensure high-speed trains do not crack the surrounding glass. Before human passengers are allowed inside, engineers run the critical first live test. A small, unmanned inspection vehicle rolls through the entire corridor, recording vibration metrics and scanning for any moisture at the joints. The successful return of that drone proves the math was correct. Hundreds of individual, modular engineering components have successfully unified to form an unbroken, pressurized shield against the abyss. Inside, the harsh reality of construction fades into a polished passenger experience. Temporary scaffolding and guardrails are removed, replaced by sleek, transparent safety barriers along the walkways. Soft internal blue lighting clicks on, illuminating the curved glass walls and revealing the drifting marine life passing just inches away from the track. And then, the first train departs. It glides smoothly down the rails, moving effortlessly through a quiet, glowing corridor entirely enveloped by the sea. While this specific megastructure remains a conceptual blueprint for now, it is a highly realistic reflection of humanity's unrelenting drive to connect distant lands. By applying strict engineering logic to bold ambition, we can take the most dangerous boundaries on Earth and transform them into voyages of wonder.